Can I start? Yeah. Okay. Hello, my name is Miss Kim, and I'm a graduate student in physics department. I'm, I'm sorry, but they have to update it. So, my major is physics. So, today's topic is kind of a little bit physical. So, today's topic is realization of quantum computing, circuit QED. So, today's topic is circuit QED, and is simply how to make a cube, how to realize the qubit. Let's start. Oh, okay. So this is the content table. So first I will introduce the circuit QED, and because in the circuit QED we use superconductor, so I will give you a brief introduction of superconductivity. And to understand the circuit, so we need quantum mechanics. So I will give quantum mechanical description of the circuit, and finally I will talk about transmon. The transmon is the transmon will be used for a qubit, and the light mirror interaction is used for the control of the qubit. Okay, introduction to circuit QED. The circuit QED is the one of the most powerful candidates for realizable quantum computing qubits. So the circuit QED has similar analogy with the cavity QED. The cavity QED is my last topic, and make qubit and control the topic is make qubit and controlling. So the qubit will be the qubit, and we control the qubit by using the electromagnetic wave. And also the electromagnetic wave is light. And instead of cavity QED, in the circuit QED, we use superconducting resonator will be used. I will talk about later. And many kinds of superconducting qubits are studied, but like charge qubits and phase qubits and quantronium and another qubit are also candidate, but in my talk, I will focus on transmon qubit. It has long coherence time. The coherence time is most important topic to realization of qubit, and it is easy to control. In my presentation, the reference is this paper, circuit quantum electrodynamics, review of monophysics. It is very recent paper. Okay. Before the circuit QED, I will give a brief, very short brief review of cavity QED. There are atoms, and atoms are interacting with photons. The photon is just light, and the atoms are confined in cavity. So by using the property of light, atomic qubit can be controlled. This is the conceptual picture. There is an atom, and the atom have two levels. The two level is used for the qubit. And the light can change the level of qubit. So we can control the qubit. So, and I will give a very short introduction of superconductivity. Maybe most of you are, maybe your major is electrical engineering, but maybe I think you have know about superconductivity. Am I right? Okay. below the critical temperature, the resistance drops to 0 suddenly. It's just, this phenomena is observed in experimentally about 100 years ago. So below the critical temperature, the resistance drops to 0 suddenly. So to understand the superconductivity, we need about quantum mechanical and quantum many-body theory understand theory, but I will not give you this description. Just I will give you phenomenological and macroscopic theory. Okay, I will give you this. So for the understand superconductivity, the well-known theory is BCS theory, but this explanation is very hard, so I will not give you the introduction, and I will give you just simple macroscopic phenomenological theory. To understand superconductivity, we think about just macroscopic wave function. This is just wave function. It's just density, and this is just phase. Okay. If you have any question, you can raise hand, please. Similar with the momentum and position, x and p, the number and phase is conjugate variable. Simply, I will give you explanation. This is psi and psi dagger. Quantum mechanically, the commutator is 1. This is just definitions, by definition. And just simple calculation, we can write like this, and this is just 1 because this is 1. So multiplying E over E to minus I theta, you can like this. This can imply this one. It is very similar to X and P, momentum and position. So maybe you are familiar with this. Momentum operator is derivative of space, partial derivative. So maybe you are familiar with uncertainty principle. Momentum and position is uncommutable. So this uncommutable property derives the uncertainty. Therefore, we can think about the uncertainty of number and phase, the particle number and the phase. In the superconductor, the phase is, we can choose phase. Chosen means we can know the phase. So the uncertainty about phase is 0. So the uncertainty about number can diverge. This make the superconductivity, because the number uncertainty of number means the uncertainty of number is diverged. So number can change. So the current can flow without resistance. Oh, okay. Next. And I will give you brief introduction of Josephson effect. A supercurrent can flow through can flow through thin insulator. It's just quantum mechanical effect. You can imagine the quantum tunneling. The very important thing is the Josephson effect, the tunneling through the insulator. And the current is obtained by the phase difference. superconductor 1, superconductor 2, the superconductors have different phase. The kind of phase phi1, phi2, the phi is phi1 minus phi2, just phi1 minus phi2. And if the phase has time dependence, there is voltage difference. The voltage difference can be calculated by the differentiation of the phase. And the Josephson junction has the Josephson energy. This is just analogous with the insulator. Sorry. So the magnetic energy in the solenoid. This is just power of the electric field. And by using the definitions, we can write this integral. So the integral of sine is just cosine. This is just Josephson energy. In summary, between the superconductor, there is an insulator. Because of the quantum tunneling, the current can flow. And this is like just the solenoid 뭐라고? 그 뭐냐? Just it has wall about inductors. So this has electromagnetic energy. So I will give you the quantum mechanical description of circuit. Just in low temperature, maybe you are familiar with harmonic oscillator, okay? However, in quantum mechanics, harmonic oscillator has different behavior with classical model. Also, circuit has quantum mechanical description, and I will give you how to quantize the circuit. Let's think about the energy. Is it just charging energy in capacitor and magnetic energy in inductor? Okay. Now, I'm sorry, but it is a little bit physical. In this Lagrangian, we can think about conjugate variable. So this is charge, and the conjugate variable can be calculated by the partial differentiation. So we can define the conjugate variable of charge, and this is just current. So maybe we will know about that. Momentum and position has like commutation relation because they are conjugate variable. In this case, instead of momentum and position, charge and current is conjugate variable, so they are not commute. So the Hamiltonian is like this, and maybe you can think about this is just X, and this is just P. This is very similar form with harmonic oscillator, so you can diagonalize it by the ladder operators. So this is the quantum mechanical description of circuit. In the quantum mechanics, just LC circuit has discrete energies. So this energy mode is just photon, because in the LC circuit, there's electromagnetic wave. Electromagnetic wave is oscillating, and those oscillating electromagnetic wave is just light and photon. This is just photon energy. In the previous slide, I will talk about just one LC circuit, but in real world, the circuit has finite size. The finite size circuit can be described by series connected circuit. So you can think of a series connected circuit, and by using just Fourier transform, you can think about this circuit like the sum of normal mode. I think it is a little bit hard work, so I can go next. Okay, let's think about transform. To operate as a qubit, we need only two energy levels. Okay. However, harmonic oscillation has constant energy level spacing. H bar omega, 3 H bar omega, 3 H bar omega. It's not good. However, the Josephson energy has unharmonic term. This is just cosine. Because if cosine is small, you can tell expansion 1 minus x squared. The x squared is harmonic term. However, the cosine is not harmonic. So because of the cosine term, the system can be non-linearity. So therefore, the energy level spacing is not constant. Okay. So the ground state and first excited state are used for qubit because of the energy level spacing is not constant. This ground state and first excited state is called transmon qubit. Oh, and the Josephson energy is larger than charging energy. The device is independent of gate charges. So this means the device has long coherence time. So I will give you how to control the qubit. There's circuit. There's circuit. It has role like cavity, and there's transmon qubit. The transmon qubit and the circuit can have interaction. So this Hamiltonian is a little bit complex, but I want to talk about that. The transmon and circuit can interaction, and by controlling the circuit, you can control the transmon qubit. This is just take-home message. Oh, this is the real picture about transmon qubit, and the Google is making the transmon qubit. The name is Google XMO. Okay. This is my presentation, and thank you for listening. I'm sorry, but it's a little bit very physical. This is just take-home message, but it is the transmon, the two levels, and this circuit is electromagnetic wave. So electromagnetic wave is light. The light and transmon qubit can interaction. So by changing the light, you can control the transmon qubit. This is just qubit operator.
Thank you for the presentation. I think it was a very good introduction. Any questions?
I think this is out of scope of the presentation, but I'm just curious. So how do you create entanglements between?
In my previous talk, I will talk about capital QED. So let's see like the picture. There is a transmon. Okay, there are transmons, and there are circuits. So you can control the circuit simultaneously. Okay. So you can think about CNOT gate. So people there are separated by operate CNOT gate. You can make integer state. In this picture, there is just one transmon qubit. However, in real world, you can think about multiple transmon qubit, so you can make entangled state.
Like using the light to create manipulate the state of the qubit, right? What property of the light do you like match with the, for example, if you want to apply some sort of rotation to the qubit?
Sorry.
For example, if you want to apply some sort of rotation or maybe flip on the qubit,
Okay.
what property of the light are you going to parameterize?
You just talk about how to couple the qubit and light.
Yeah.
This is resonator. In the resonator, this is just LC circuit, and there is electromagnetic wave. Okay, this is light. Okay, and there is transmon qubit. Okay. You can see this line. There is two metal. So between the metal, there is charging energy, because this is play like capacitance. So this term means the capacitance between the circuit and transform. This is interaction term. So by controlling the number of photon, you can change the state of transform.
So you control it by the charge on the capacitor.
Yes, a charge of the third resonator. This topic is very well explained in the reference, so I'm not studied about this readout of the qubit and controlling the qubit. I'm sorry.
So I can see how the math goes when you talk about perception function. But how is it really related to perception?
I skipped the theory of Cooper pair. In the Josephson effect, there is quantum phonon. And exactly, I took, I can, exactly, the Cooper pair is tunneling.
That is like adapted in the equation and
This formula implies the tunneling of Cooper pair, but I will not give you the detail about this. But if you want, I will give you a very good reference book.
yes, please.
Oh, are you interested in quantum many-byte theory?
A bit like up to the introduction, like
So certain,
I thought the quantum effects are related, being Cooper pair being like boson. So, but I don't know exactly why and how.
in the BCS theory, because of the phonon, not electron, the electron and electron can have attractive interaction. This may prepare. You heard exactly. Electron and electron can have attractive interaction because of the phonon. I will skip it.
That is what very basic idea.
Wave function? Yes, yes. Why do you use scale and
Because psi dagger psi is density. Okay.
As far as I know, so the known strategy, like no qubit implement strategy like by quantum tweaking, which is using IBM or ion traps are suffering from the qubit proximity problem, which means you have to make an entanglement. The qubits must be cross each other. So this strategy will suffer for the same problem or not?
I'm sorry, but I don't know about details, but
Yeah.
I just heard about the trans-1 qubit is most powerful candidate for the quantum computer. So the proximity problem is also considered. I just in my memory. So, but I don't know about exact benchmark or
Some comparisons.
comparison is I don't know about it. Sorry.
In the last slide, almost last slide, you show the Google's transform data.
Yes.
And like compared to IBM's quantum machine, like IBM has a resonator, but it's like evolution, like innovation.
What? Okay.
But in that picture, it doesn't have any like particular shape. So can you
Exactly, the X-Moon has a little bit different structure of this figure. But I'm sorry, but I don't know about the IBM machine. So, yes, I'm sorry, but I don't know about it exactly.
if there's no more question, thank you for the presentation. Thank you.